Let's imagine that we take an electron beam and we shine this beam on two slits. And then we allow those electrons to come over and strike a screen over here. And we do this, we perform this experiment one electron at a time. So we send in one electron, we allow it to hit the screen. Another electron, we allow it to hit the screen, etc., etc. And we watch the pattern as it builds up on the screen, electron by electron. What would that look like? These are some images that are on Wikipedia that are used with kind permission of Dr. Tanimura. This is the image that is created after 11 electrons have struck the screen. What do we see? Just individual dots where each dot represents the collision of one electron with the screen. So we can see that this pattern is being built up electron by electron. Now, what if we add some more electrons? This is the image that we find after 200 electrons. Obviously, we see them scattered all over the place. Here is the image after 6,000 electrons. They certainly look random, however, we might be seeing a pattern kind of developing here. This is the image after 40,000 electrons, and we are definitely seeing something starting to emerge here. And here is the image after 140,000 electrons, and we definitely see something going on here. We see very definitely many more electrons colliding in this area, this area, this area, this area. Fewer electrons here, here, here. Well, what's going on? This certainly looks like something we've seen before. We've got constructive interference going on here. We've got bright fringes. We've got dark fringes where we must assume we've got destructive interference going on. So somehow the electrons have a wave-like nature that is giving rise to constructive interference and destructive interference. Let's go back to our picture of the experiment and let's think about what's going on. If electrons are demonstrating a wave-like behavior, then they must have a wavelength. So what wavelength do the electrons have? What wavelength do we have for matter? Well, this was put forward in 1923 by Louis de Broglie, and what we now call the de Broglie wavelength. But this is a wavelength for matter. Well, basically we use the same equation that we used for the momentum of light, which was h over lambda, or lambda is h over p. So the wavelength, the de Broglie wavelength, is h over the momentum of the particle. In other words, h over mv. Well, let's stick some numbers in here. What kind of wavelengths are we talking about for some matter, moving matter? Let's figure out what the de Broglie wavelength is for, say, some ordinary, everyday sort of thing, like maybe a paperclip. Let's imagine we have a mass of 1 gram and maybe moving at 1 meter per second. So what kind of wavelength are we talking about? Well, lambda is h over mv. H, 6.626 times 10 to the minus 34 joule seconds. M, 1 times 10 to the minus 3 kilograms. V, 1 meter per second. What do we get? 6.63 times 10 to the minus 31 meters. Well, let's think about that distance. That is extremely small. The nucleus of an atom is on the order of 10 to the minus 15th meters. Well, this is another factor of 10 to the minus 15th times that size. So it's 10 to the minus 15 nuclear sizes. That is something that we would never be able to measure. Totally outside our experimental range of verification. However, if we look at a smaller object, like an electron with a mass of 9.11 times 10 to the minus 31 kilograms, a speed of maybe 1 times 10 to the 6 meters per second, a very reasonable electron speed, we get a wavelength of h over mv of h over 9.11 times 10 to the minus 31 kilograms, v 1 times 10 to the 6th. We end up with 7.29 times 10 to the minus 10th meters. Now again, that's very small. However, it's on the order of the scale of atoms, which is where electrons hang out. So this type of distance scale will definitely have an effect on the behavior of electrons. This would never affect the motion of a paperclip, but this will have a very, very dominant effect on the behavior of electrons. anything even larger than a paper clip and larger speed, we're going to have an even smaller wavelength. So this is not the kind of thing, the de Broglie wavelength is not the kind of behavior that would affect any macroscopic sort of object. It's only going to affect things on very, very small scales, on the atomic scale. Okay, let's go back to the electron double slit experiment just for one more second. So here's our double slit over here, and here's our screen over here. We've got the electrons coming in here one at a time, going through the slits and striking the screen over here. Now, it's tempting to think of these electrons coming in. Here's an electron coming in. Now, what's that electron going to do? Is it going to go through the top slit, or is it going to go through the bottom slit? Well, let's keep in mind, the pattern that was built up over here was built up electron by electron, which means we had to have this interference going on. Well, what is one electron going to interfere with? Well, an electron that goes through the top is not going to have anything to interfere with going through the bottom. If it goes through the bottom, there's nothing going through the top to interfere with it. So what does an electron have to do? Well, we have to not think of an electron as this little particle, like a little ball that comes in and goes through one slit or the other. If we were to cover up one of these, we would not get a double slit interference pattern. We would get a single slit interference pattern. So that electron has to be able to go through both, and one electron does go through both slits. In a manner of speaking, we have to think about it that way. This wave nature of the electron tells us a probability of where we're going to find the electron. This is kind of one interpretation, that the wave nature of the electron tells us the probability of finding the electron striking the screen over here at any particular point. And that wave nature probability has to be able to go through both slits. One way of thinking about it is that the electron is kind of like this electron cloud, and that cloud has to be able to go through both slits at the same time. Okay, that's a very difficult thing to think about. Well, I'm afraid that's all we have time for. I hope to see you next time.